Okay, well, welcome those of you who have made it. Welcome to virtual CoKoCon. And my presentation today is called To See New Earths. I'm getting a little bit of feedback here, so
Yeah, somebody
maybe,
might want to mute. We're getting some feedback.
Mute.
and I'll explain in quotes in a little bit, but basically I have given exoplanet presentations at Arizona conventions before. This one is focused a little bit more specifically on what we're doing at Kitt Peak National Observatory outside of Tucson, and also how our project that we're working on there is in supporting NASA's TESS mission, the space telescope looking for exoplanets. And let's see, maybe I need to be, there we go. Taking a minute to change slides. So, my name's David Lee Summers. I am an author and an editor. I'm an author by day, and up on the screen are a selection of some of my books. I do have a space in the CoKoCon virtual dealers room. My company is Hadrosaur Productions, and you can find many of these books there. And there are what you can't find there, you can either find at Duncan Richoff's site, or you can find at a bookstore near you, like Amazon or Barnes & Noble. I tend to write steampunk, science fiction, horror, and I have a couple of science fiction anthologies that I edited with the Kepler project scientist Steve Howell, and those are A Kepler's Dozen and Kepler's Cowboys, all short stories set around actual planets discovered by the Kepler mission. By night, I operate telescopes at Kitt Peak National Observatory, including the WIYN 3.5 meter telescope, which I'll talk about a little bit. This picture is actually in the entryway of the WIYN 3.5 meter, and the person I'm standing with there is Ethan Peck, who plays Spock on Star Trek, played Spock on Star Trek Discovery, will be playing him in Star Trek Strange New Worlds. And he came during one of our commissioning nights before the pandemic, hence no masks. And but you know, you've got a science project of some interest when Spock comes to check you out. So this project is all set up at Kitt Peak National Observatory. I imagine most of you know about Kitt Peak, but it's basically located southwest of Tucson, Arizona, off of Highway 86. Unfortunately, because of the pandemic, we're still closed to outside visitors for the time being. But during this time, there's a major upgrade going on of our visitor facilities. So hopefully when we get open in the not too distant future, you can come out and visit us. The observatory is on the land of the Tohono O'odham Native people, and we actually, the federal government actually leases the observatory from them, and that becomes important, among other things, in the name of the spectrograph, which I'll explain in a little bit. And one of the features of Kitt Peak is it is the largest single collection of astronomical telescopes on one mountain in the whole world. And we have two now kind of considered mid-size class telescopes, or the large telescopes on the mountain. Those are the Mayall 4 meter, which is the sort of tall tower telescope off in the distance in our photo here. And then the one we're talking about is the WIYN telescope, which is a 3.5 meter telescope, and it's on the left-hand side of the photo as you're looking at it. So this is what it looks like inside that sort of funny octagonal building. This is the WIYN telescope, which is one of the newer telescopes on Kitt Peak. It opened up in 1995. It has a 3.5 meter primary mirror. So that's a little bit smaller than the 4 meter, which is the biggest telescope on the mountain. but it's a fairly modern design telescope. And one of the features of this telescope is that you can actually mount 4 instruments on the telescope at one time, and literally flip between them with a turn of what we call our tertiary mirror in the center of the telescope. I don't know if my mouse shows up, but it's right here. If you look at the primary mirror, it's right in the middle of that, and that mirror rotates and can move to different ports on the outside of the telescope. WIYN features an active optic system, and by that what I mean is that there are actuators on the back of the telescope that deform the primary mirror to give us the best figure for the mirror depending on the elevation of the telescope. And it also has a tip-tilt adaptive optic system specifically in the NewID instrument. And this is the spectrograph we're using to hunt for exoplanets. Adaptive optics is where you're actually adjusting the optics of the telescope, or in this case, the optics of the instrument, to compensate for atmospheric effects. So you have the warm air rising from the ground, for instance, causes the images to shimmy and shake a little bit, and the adaptive optics attempts to correct for that. You've probably seen images of telescopes that use lasers to do that. Ours doesn't actually have a laser adaptive optic system. What it is it's what we call a tip tilt, and that's where we have a guide star, and it actually tries to keep the energy of the guide star down to as small a space on the detector as possible. So this, we just to give you a little bit of background about what kind of instrument this is, we're involved in doing spectroscopy, which is a way that astronomers do chemistry on stars, among other things. And spectroscopy as a means to chemistry was something discovered by Joseph von Fraunhofer back in the 19th century. And what you can do is you can point your spectrograph, as our gentleman is here in the photo on the left, at a cloud of gas or at a hot object. If you're pointed at just a hot, bright object like a light bulb filament, all you're going to see is a continuous spectrum, a rainbow. But what gets interesting is if you put a cloud of cooler gas between you and the bright object. If you're just looking at the illuminated cloud and the bright object isn't behind it, you'll see the series of lines, almost like a barcode through the course of, like a rainbow colored barcode through the course of your spectrum. And it turns out that what those lines are is you find out that for certain chemicals that gas may be made out of, those lines appear in very specific predictable spots, and those become essentially a fingerprint that tell you what that gas is made out of. If you look at your bright object through the cloud of gas, those lines are dark lines in the middle of the spectrum, but the lines show up in the same place in absorption or in emission, no matter what that, as long as that cloud of cooler gas is made of the same stuff. Now, while it's very interesting to know what makes that gas cloud up, the thing that's important is to know those lines always show up at the same place. So they're very predictable in their location. So when they move, and so their relative spacing is always the same with each other. And when they move, what that tells you is that the cloud of gas or the object that you're observing are basically moving away from you or toward you. And we can see this here. And what that has to do with is something called the Doppler effect, which you're probably familiar with in listening to things like trains come towards you and go away from you. It's the change of the frequency of the sound. And light does that just the same way. And what happens is if the object is moving away from you, those spectral lines, keeping all their same spacing, move ever so slightly to the red end of the spectrum if the object's moving away from you, and that's what we mean by redshift. And if the object is moving to you, you see all those lines move to you on the blue side of the spectrum. And this happens whether it's a big object moving very fast away from you, or whether it's something very small, like a planet going around a star and tugging on it. And we can actually use that redshift to detect planets. And that's what we're hoping to do with the NewID spectrograph on WIYN. Now, and as you look here, what you'll see is as the planet goes around the star, it tugs the star either a little bit towards the Earth, or it pulls it away from the Earth. And as it does that, you see the lines shift. And these are very, very tiny little tugs. And of course, how big those tugs are depend on the size of the planet. So, and basically one thing that's important to remember about that is that what you're actually measuring with redshift is you're not measuring directly the planet, but you are measuring the velocity that it's moving the object away from you. So a smaller planet moves a star less velocity than a bigger planet like Jupiter. And that's what this slide is showing now, is we see that Jupiter effectively moves the sun at 29 miles an hour when it's on the opposite side of the sun from a theoretical observer watching it from a distance. Earth only moves at 0.23 miles per hour. So as you can see in the lower image, you just kind of as a fun comparison, we compare those speeds to some common desert animals. So Jupiter is about the speed of a rabbit, whereas Earth only moves about the speed of a desert tortoise. And we need to be able to detect that. So where we come up with the NewID spectrometer is trying to detect these motions at about 0.2 miles per hour. And the whole idea is to hopefully find Earth-like planets around other stars, or follow up on them that have been detected by the TESS spectrograph. And NewID literally stands for this big, long, protracted acronym, which is NASA NSF, Explore Exoplanet Investigations with Doppler Spectrometry. And part of it is it's a clever way of using the word NewID, which is actually the Tohono O'odham word meaning to see. So that's where that acronym comes from. And like I say, the goal is to detect Earth-sized planets around sun-sized stars where possible. So the WIYN telescope has a history of supporting the Kepler mission. And what we see here is a picture of the WIYN telescope down in the lower right-hand corner of our right-hand picture. And the kind of shape up in the sky is the field of view that was of the Kepler telescope. So basically, it's just an illustration of WIYN looking at the Kepler field. But we have another instrument on the telescope called a speckle interferometer that's actually a real high-speed way of imaging stars. And it's been used to image many, many of the stars found in the Kepler program, and to actually resolve them as whether they're single stars or binary stars. And so what we've actually found from that research is we estimate that nearly half of the exoplanets we've discovered are actually in binary systems. So that's systems with two stars. And for those who know my younger daughter, Verity, I know Dee knows Verity well. That's actually what she spent as her summer job this last year, was actually investigating whether there are any biases in the data of finding Earth-like planets around binary stars. And she did that as a NASA internship this year and actually working with data from this particular project. So of course, when we're looking at these, looking for these tiny shifts in spectra, these really are very tiny. They're literally you're talking about shifts in the spectrum that are almost the scale of the atoms that make up the detector. And so to try to calibrate something that precise, there's actually this Nobel Prize winning technology, which is what they call a laser frequency comb. And so each spectrum we're taking with NewID, we take the spectrum, which you see in our bar, a little slice of a spectrum, which is just a little slice of the red part of the spectrum. And you see a couple of absorption lines in there in the right. And then on the left, all those dots are calibration lines. And to give you an idea of how tight the calibration is on this, those are 0.024 nanometers apart, each one of those little dots on that calibration comb that's coming through, so that you can then calibrate how far the lines, the absorption features, move relative to those calibration comb dots, and measure that really precisely. So of course, we want to be careful about this kind of process. Is very sensitive to temperature, pressure, even as the instrument ages and it expands over time, it's going to cause problems. And that's why you actually want to have the calibration be taken at the very same time as you're taking all of the data. So this is actually the calibration comb is basically light that we're seeing at the same time as we're taking images. And yeah, so as I say, we're looking for wobbles in the star that are on the scale of femtometers. So that is about the size of the atoms that make up the detector. So of course, getting extreme position is not just calibration, but it is actually a matter of making sure the instrument is as stable as possible. And this is what the instrument actually looks like. It sits in a clean room that we are more and more open from right to left in this set of images, but basically the rightmost image is looking down into the spectrograph. The center image is what all of that is mounted into in a clean room in this very stable, almost coffin-like device that's kept at a very constant temperature, thermally controlled. The whole table is shock controlled. You keep dust out of it, you keep moths out of it, you keep the temperature as stable as possible, and then you seal the whole thing almost up in something that I like to call a sarcophagus, because that's just what it looks like. And really, all of us who work with the instrument pretty much keep our hands off this part as much as possible. It's just, we try to seal everything up as much as we can to get that extreme precision. Now, of course, we have to get light down into this, and that's where we're actually on the telescope. And so now the place where the light comes in is, if you look at the image of the telescope, if you can see my mouse, I am circling, but it's this instrument that actually says NewID on the back of the telescope. It's at what we call the folded Cassegrain port on the telescope. And this is what we call our port adapter. And that's where the fiber and where the calibration lamps are located. And that is where the guide cameras and all of that are mounted to the telescope. And what happens is, inside that box is basically the one end of a fiber optic that runs down to that sarcophagus 2 stories below and carries the light from the star that we want to measure And this picture shows the instrument's project scientist, Sarah Logsdon, and what she is holding there is the fiber that actually carries starlight down to the instrument. And she's actually standing up by the telescope, and what's happening is someone downstairs is shining a flashlight through the fiber. So this was done during our installation. So she's smiling because we did, in installing the fiber, we didn't break anything. We're getting good light down to the instrument and back up, which means we'll also get our calibration light down there. So we actually got first light on this instrument in the fall of 2019. And here we see all of us, several of us gathered around a laptop, which was our temporary station for getting in the first image from the spectrograph. And of course, this is always a nervous moment. And here we're all happy seeing the light come through. And I'm standing there in the image. And what do we see on the screen? That is this image, which is an image of 51 Pegasi, which was picked for first light because it was the first sunlight star where an exoplanet was found back in 1995. And there again, you see examples of real spectra compared to the laser comb. And what you see is this is what we call an Echelle spectrograph. And all that does is, of course, you're probably familiar with a rainbow that runs from red all the way over to violet. What we're seeing on the image is you see red at the top, and then it runs all along red. It runs, and basically imagine that it's the different parts of the rainbow stacked on top of each other from red to violet. So we see an expansion of the red end of the spectrum, and we see an expansion of sort of the middle, what we actually tend to refer to as the yellow end of the spectrum. Of course, it's green on here, and you see those absorption features compared to those really tight laser combs. Now, of course, what happened is we were commissioning and getting data in, we commissioned the instrument in the winter of 2019 and 2020. And right up until about March of 2020, we had pretty much finished commissioning the instrument, and then we all had to shut down and go home. A lot of people think of astronomy as this very solitary exercise with an astronomer sitting out at the eyepiece at the telescope, and why do you need to social distance? Well, when you're commissioning a telescope in the modern world, it's really a lot of people sitting packed tight in a room with looking at computer monitors, and that just wasn't going to work in the era of COVID. So we had to figure out how to do things safely. As it turns out, some issues were discovered during the first wave of instrument commissioning. So during the time we were shut down and figuring out how to operate safely, Chad Bender, who is one of the instrument builders, who's sitting there with the Arizona shirt over on the right-hand side of the photo, came up and did some work on the instrument. And then we figured out how to recommission the instrument and do it again. So we actually commissioned it twice. We commissioned this winter, and this time it was me working alone in this control room. The NewID observer working in a different building on the mountain, and then all of these other people who were in the room were working remote from their homes, pretty much in Tucson. And but doing that, we were successfully able to commission the instrument. We have actually, as of July of this year, it has passed its operational readiness review. So we had the challenge of commissioning during the pandemic, and we will probably talk about that even more during our Science of the Pandemic panel tomorrow morning. But the picture here is just showing the star Tau Ceti, which is a very stable star, and it's just showing that the radial velocity measurements for that are proving very, very stable. And basically, we see we're actually, the measurements are better than, are stable to better than 50 centimeters per second. Let's see, get my.
That was a good segue, David, with the the pandemic one.
Thank you. Now, one thing that's cool about NewID is we're actually getting some bonus science, and even during the pandemic, we were doing, even though there was about an 8-month period where no live science or with observers was happening on the mountain, we actually were able to get some bonus science. And a little telescope built up on the corner of the WIYN telescope, and it's a periheliometer, which just is a fancy name for it's a telescope that does nothing but track the sun. And it's been feeding light from the sun to the NewID spectrograph. And as it turns out that during the pandemic, NewID ended up producing the highest resolution spectrum of the sun to date from any spectrograph anywhere. And people might be familiar with the McMath telescope on Kitt Peak. And there's famously, it was the telescope that had the record for the highest resolution spectrum of the sun. Now our little solar telescope has actually beaten that. And the name of the game sometimes isn't size of the telescope. You can make a bad joke about it's not the size of the telescope, but how you use it. It's not the size of the telescope, it's resolution in this case. And it's because this spectrograph has such high resolution. We have now a lot of detail about, and like I say, what you can do is with using a spectrograph, you get a lot of the chemistry of the atmosphere. So we now have a lot more detail about the atmosphere of the sun than we did before, all because of NewID and all because of just someone had the idea of putting this little sun spectrograph up on it. And of course, it's also used for calibration with our instruments, because of course, if we're trying to understand other stars as whether they're sun-like stars or not, we want to understand how much they're like our sun. And it's a good idea, good data of our sun through the same instrument that you're using to compare it to. So that's part of the reason that this is there. Now we're going to kind of quickly talk about TESS, the Transiting Exoplanet Survey Satellite. Ostensibly, NASA funds the NewID spectrograph in support of TESS. And one thing, I think I just very quickly mentioned it, one of the things you learn from the radial velocity method, because it tells you how fast the planet pulls the star, that becomes, if you know that and you know the distance from the star, you can actually calculate a mass of the star. And that's one important quantity. TESS, the Transiting Exoplanet Survey Satellite, was launched in April 2018. It uses a different method for looking for planets around stars. It actually looks for what we call transits, which are basically looking literally for the little minuscule amount of light that's dropped from as a planet goes across the surface of the star. Its science operations began in July of 2018. It surveyed the nearest 500,000 stars. It actually completed its primary science mission in July of 2020, and it's still going on with an extended science mission now. But so far, it's discovered 148 confirmed planets and over 4,436 planet candidates. And TESS, Kepler, as I alluded was looking at one spot in the sky, and it didn't really care whether the planets were close to us or far from us. What it cared about was that it was looking at a part of the sky which was known to have a lot of sun-like stars. And so it was just trying to see, just get an idea how many stars might have planets. TESS is actually tasked at looking at all the nearest stars. So what gets interesting here is these start to get to be the ones that we might conceivably, in the time that humans are around on Earth, might get a chance to know more about and maybe visit and learn more about in some way or another. I already mentioned it's in its extended mission, and it's a successor to the Kepler mission using the transit method. And as I already said, what we do with the transit method is we're looking for the change of light as the planet crosses in front of the star. Now, as it turns out, this becomes a way you can actually get an upper limit for the radius of the planet, for the diameter of the planet, because the planet is so close to its star relative to us. We're talking tens, hundreds of light years to the star and the planet, whereas they're light minutes maybe from each other. Effectively, you can actually just do a ratio. The amount of light that it drops basically gives you the size of the planet. So of course, a Jupiter-sized planet will drop the light of the star a lot. An Earth-sized planet drops it just a little bit. Now, of course, one of the key things we're looking for in exoplanet science are stars in the Goldilocks zone. This is something that gets talked about a lot. Of course, we're looking for those planets where the conditions are just right for life. It's not too hot, not too cold, and pretty much how we define that is we're looking for planets. The definition is planets that are sufficiently far from the star that water will stay liquid on the surface, but not so far away that it will be frozen on the surface. And of course, where that zone is and how close it is to the star depends on how hot the star is. So for cooler stars, the so-called Goldilocks zone is a lot closer to the star, but for hotter stars, it's a lot further away. So confirming planets, NewID's job will be to follow up on planet candidates to confirm discoveries. We'll get additional information. Like I said, the transit method gives us a good diameter, but the radial velocity method gives us a good mass. And with the two of those, you can get density, and that tells you whether you're looking at a rocky planet or a gas giant planet. Pretty much, sometimes you'll see artists' conceptions of planets, and I'll have a few here to wrap up the presentation, but we really don't know that that's what the planet looks like. What we know is that it's a rocky planet, it's a gaseous planet, it's what we call a super Earth. It's maybe it's got the density mostly of ice, like Uranus and Neptune do. So the other thing to remember about this is, of course, so far TESS worked for 2 years. In a 2-year survey, think about the Earth going around the sun. That's that's only 2 turns of the Earth around the sun. It's hard to see a lot of Earths and get more than one rotation and confirm it really exists and confirm its orbit in only 2 years. So the idea behind NewID is it can follow these systems a lot longer than the space-based telescope can, because it's inexpensive to operate. All the infrastructure is already there, ground-based telescope. So just kind of to segue into a little bit of how many planets there are, and this just always blows me away because the numbers increase every time I give an exoplanet presentation. I grew up in an era of there only being 9 planets. I spent several years working at New Mexico State University and even worked alongside Clyde Tombaugh, who discovered Pluto. And so I am a Pluto as a planet. Yeah, it's a dwarf planet, but I think dwarf planets are planets too. So, but 9 planets. And now we're actually at a point where we have 4,466 confirmed planets around 3,309 stars. And the source of this is the NASA Exoplanet Archive. The vast majority of these are discoveries from Kepler and TESS at this point. We now have 35 confirmed planets in habitable zones by temperature. Not all of these are Earth-sized planets. Some of them are kind of Jupiter-sized planets, but moons around those could be interesting too. The largest number of planets we have in a system is 8. So for all intents and purposes, that's about like our solar system, but we'll talk about that one in just a minute. We currently have over 1,300 confirmed planets that have radii less than or equal to 2 Earth radii. So we have a large number of smallish planets. We have 90 planets with masses less than or equal to 3 Earth masses. So those are planets that start to get in. When you take the intersection of those start to be planets that are looking a lot like Earth. And the intersection is we have 39 planets in which both conditions are true. We have low mass and small radius. So not a lot, but still 39 Earth-sized planets out in the galaxy so far, and many, many more, I'm sure, to come as we spend more years monitoring this. So let's look at that 8-planet system a little bit. So this is the Kepler 90 system, and of course it's an artist concept, and here we see our 8 planets of the Kepler 90 system with the 8 not dwarf planets of our own solar system. And you kind of see a distribution of the ones in Kepler 90 are maybe just a little bit bigger overall than the planets in our system, but it's maybe not so different looking at it from our system in terms of planet radius. But there is one big difference that we see in this image. This is basically comparing the Kepler 90 system on the right-hand or on the left-hand side, sorry, to our solar system on the right-hand side. And what you find is all 8 planets orbit in an orbit around Kepler 90. Their orbits are all within the orbit of would be within the orbit of Earth if the star were in the same place. So it's not quite the same kind of system, and you've got some planets in very tight orbits around that. So it's easy to look at some of these numbers and say, oh, we're getting some very solar system-like things, but we're actually discovering some of these systems, for whatever reason, form very differently than our system did. And this is an example of one with many planets, but they're all the closest planet has about a 1 year, or the out planet is much closer to Earth's orbit. Now let's kind of look at a few of these that we're coming up on that are starting to get to be interesting planets. We have the GJ 357 system. That's 31 light years away. So it's not one we're going to get to probably in our lifetime, but it's the star is an M dwarf, which means it's a little red star. It's about 40% fainter than our sun. Planet D going around that is about 6 times Earth mass, so what we might call a super Earth, but it is in the habitable zone. And so, if you have water on that, it might be a candidate for being a planet with life. The L9859 system is kind of an interesting one. So far, one of its planets is the smallest one discovered by TESS, which is actually between the size of Earth and Mars. Mars, of course, is much smaller than Earth, so it's kind of exciting to start finding planets smaller than the Earth. This planet orbits an M dwarf, another small star, 35 light years away. And of course, you'll find many of these discoveries, many of these planets orbit M dwarfs. And part of the reason for that is because, of course, going back to what we said about the Goldilocks zone, small, cool stars, the planets have to be closer in to be in the so-called Goldilocks zone. So you're going to find around these M dwarfs, you're probably going to find the planets in a little bit closer than you'll find them around a star that's more like the sun. Another M dwarf star, TOI 700. Again, we have a planet in the habitable zone, planet D, which is about 1.6 times the size of the Earth. This is now 100 light years from Earth, has 3 planets in the system so far. And, but yes, it's in the habitable zone, but it has a 37-day orbit. And to put that in perspective, of course, Earth has a 365-day orbit. Mercury has an 88-day orbit. So to be in the habitable, it's just on the inner edge of its habitable zone, and it's got this, just whips around with a 37-day year. I think my years go way too fast. Would be incredible there. TOI 1338 is TESS's first planet that was discovered around a binary star. The planet is around the size of Saturn, and it orbits the pair of stars every 95 days. So again, remembering what I said, Mercury orbits in 88 days. So this is a very Mercury-like fast orbit. One of those stars is an M dwarf, but the other is a G dwarf like our sun. And the M dwarf actually whips around that G star every 15 days. Now, one thing that I'm asked about in exoplanet presentations, and we're starting to get a little bit of a handle on, this is actually related to some of the work my daughter did, is, do planets orbit the pairs of stars, or do they tend to orbit one of the stars of a pair? This one is obviously, and I think the answer is both. This is a classic case of a planet orbiting both stars of a binary system. But if you actually look, so far, that's a little bit of a rarity. It turns out that most of the cases of planets we find in binary systems, the planets orbit one of the stars. And most cases, these are fairly wide binary pairs. So pretty much when you start forming planets in binary systems is when the two stars are separated by a distance that's comparable to the distance between the sun and, say, Neptune. And that's when you start seeing planets around one of the stars. Now, we don't know yet whether we don't have enough data about these yet to say that that's like a feature, or if that's just a selection effect of how we're doing the science. And that specifically was one of the things my daughter was looking into to try to figure out what questions to actually ask and what systems to look at to try to further that particular science. So that's pretty exciting stuff. Another, this was actually in the news not too long ago, another interesting system from TESS is what we believe are sibling planet systems. And this gets interesting when you're trying to understand how planet systems form from different stars that formed at the same time. We think these two stars that are about 130 light years from us probably were formed at about the same time in the same stellar cloud. We think that because they're basically moving in the same direction away from us, they're basically moving parallel to each other, and they seem to be, and pretty much they're very similar types, very similar spectral types, and both of them have planet systems, and they're of a similar age. And these are about 5% the age of our sun. So these would be probably much earlier planet systems than we're seeing. And they're separated by a distance of 30 light years from each other and about 130 light years from us. So just as far as what kinds of planets are we discovering so far, this is just kind of a breakdown. The number here is different than I showed earlier, which was closer to 4,400 confirmed exoplanets. That's just because the slide is a little bit older, but the ratios are still about the same. Basically, if you look Neptune-sized planets, gas giants like Jupiter, super Earths, which we really don't have in our solar system, which are basically, I believe the cutoff is like 3 times Earth's radius, and terrestrial. Those classes of planets, the bigger planets, are kind of equal numbers of discovery. Terrestrial planets seem to so far be kind of rare, but that again may be more a selection effect than it is an actual real statistics so far, just because the smaller planets are harder to see both in both methods, whether you're using a transit method of discovering planets or whether you're looking at a radial velocity with spectra. So there are some resources here, and once I've presented this, I'll open things up for some questions if anyone has any. Basically, these are some places you can get a little bit more information. There's a website that you can read more about the TESS spectrograph. It's at nasa.gov site, content about TESS. There was an article at the Planetary Society that was a really good background about NewID that I thought talked a lot of, had some really good stuff about what we're doing and what we expect to do. Of course, the NewID spectrograph is really just, like I say, it was just July that we were approved for science, the science mission. So I will probably have a lot more of NewID's actual science next time I give this talk at a CoKoCon. You can learn more about me at davidleesummers.com. And in fact, if you want to be involved looking for planets, there is actually a way to get involved with looking at TESS data. Like I say, there are thousands of these exoplanet candidates. Sorting through that data is a major job. It's a combination of people using artificial intelligence algorithms on this data, but also, you know, if you want to go in and dive in and start seeing if you're seeing evidence of eclipses in TESS data, you can go to planethunters.org, and there's a little training program there that it runs you through, and then it starts passing you on actual bits of data to flag as having potential eclipses to be seen in it. And in fact, amateur astronomers, citizen scientists working through planethunters.org have actually discovered planets using with Kepler data. So that's actually a way you can come in and make a contribution. So thank you all for listening. It's good to see some of your faces in the cameras, and thank you for your attention. I hope we get to do this in person at some point in the not too distant future.
That would be wonderful, David. Does anybody have any questions for David? Oh, there's one in the chat. Chris asks, I just heard about a new type of world called Hycean, bigger than super Earth, but smaller than mini Neptune. Can you tell us something about those?
Okay, that one is a new name to me, but it's, I imagine reclassified, so the short answer is, unfortunately, I can't tell you any specifics because that's new terminology to me. But as far as to get a new class, part of where the Neptune size and the super Earth size tend to break down is super Earth size worlds. There are what we tend to classify water worlds by density, and we tend to classify Neptunes by density, and it's kind of ice density compared to water type density. I imagine these Hycean worlds must be either, must have a different density from sort of water and ice, maybe a rocky type density in a very large size. So yeah, I'll have to look that up and see what I can learn about it.
So when you discover these planets that are orbiting a star, how, I get how you can see that they're there by the shadow, but how do you actually see the composition of the planet? Or you are seeing the composition, right?
So we don't see the composition. What we get is that with the transit method, we see the size of the planet, and with the radial velocity method, we get a mass. And really, density of the planet can be taken just from dividing the two. So what we get is a density. So you can compare the density to rock, you can compare it to water, you can compare it to gases, and so we don't get a specific composition. We get a density. We can say the planet is like this because of the density. Now, this is where a space telescope like James Webb will come in, will be a lot more interesting, especially with some of these planets that are, on the scale of 30 light years away. That's getting to the point where a big space telescope with high resolution like James Webb might actually start being able to take direct spectra of the planets and of their atmospheres. And then you can start actually saying, this is what the gas in the atmosphere is actually made of. We're not there yet, but that's one of the things that's hoped for with JWST when it launches, I hope soon.
Allison and Mike ask, is it NEID? Is that NEID?
It's pronounced NewID.
NewID, okay. There. Is NewID sensitive to pick up exomoons, or would those need to be planetary scale themselves?
Good question, and the answer is I think I don't think NewID it would be, because that would be trying to get to the effect of the gravity of the moon on the planet. We're already sort of right at about the limit, seeing Earth-sized planets going around stars. Now, if, say, you should happen to have an Earth-sized moon going around maybe a Jupiter-sized planet, I don't know. My guess would be that would probably be lost in the noise, but you'd probably have to be in that size scale before you could begin to detect it with NewID.
So
I see the link for the Hycean planets here, so thank you.
So on the when that first planetary system you showed us that had basically all the planets within the orbit of Earth, are any of those in the Goldilocks zone, or is?
Yeah. So actually, in that case, some of the middle ones are in the Goldilocks zone on that one, and most of those are going to be sort of Neptune-sized planets. But again, those can be interesting because those size planets might have moons that could have liquid water on them. I think we're officially at time, but if there's one more question, I can see if I can answer.
Anyone? Oh, Chris has got his hand up. You'd have to unmute, Chris, if you have
Sorry. I was just a clapping thing. But I want to thank you for the
Oh.
speech. Thank you for the talk. That's all.
Well, thank you all for attending and coming out first thing on Saturday morning. And like I say, I hope we'll get Kitt Peak opened up in the not too distant future, and maybe you all can come visit, and hopefully we can all start.
I would love to come visit you up there. I have not had a chance to do so yet.
Yes, absolutely. We, right now, like I say, it's getting lonely up there. There's not many of us up on the mountain right now.
Thanks, David. This is really interesting. I appreciate you doing this.
Well, thanks all for coming.
Yeah, keep in mind, David has some other, he's got the one Science in the Pandemic. If I get the title wrong, I'm sure.
Right.
Check your programming.
Dr. Dave and Catherine Asaro.
Hopefully, she was having some computer problem. I think her computer crashed this morning, so she was trying to borrow her daughter. So hopefully she managed to get that all taken care of. I haven't heard otherwise, so that's good.
And then in I think it's about an hour and a half, I am talking about Weird Westerns, sort of really shifting gears with Jeff Marriott.
Yeah, and that will be on Discord.
Yes.
Yes. Has everybody got their questions out? Yeah, nodding.
Okay. Well, thank you all.
Thank you, David. We look forward to seeing the rest of your panels, and I'm going to end the meeting, everyone.